Okay, so this is the 5th lecture, and we could divide the material of the past 2 weeks into, I mean, it's all connected, but one way of dividing it would be into 2 blocks. So far in the course, we had in lectures 1 to 3, we had the notion of computability induced by a Turing machine. So this is a fundamental notion of algorithm, so to speak, and we could say that then our notion of computability is modeled by the Turing machine computable functions, although of course we were also equally interested in languages, but let's for today restrict to functions. And the general level that we had in lecture 3, they were partial functions from words over one alphabet, sigma 1, well, that's always the alphabet's are finite, to words over another alphabet, sigma 2. That was the very general form we had. And then another way of looking at last week is that the definition, the self-contained definition of the partial recursive functions gives us a completely different definition of computability. So lecture 4 provides a different definition, and the fundamental notion is the notion of partial recursive functions. And the natural way of modeling these is partial functions on k tuples of natural numbers. So from k tuples of natural numbers to the natural numbers, and that's for all possible arities k greater than or equal to 0. One needs to consider multi-argument functions because the whole way in which we define the partial recursive functions is via these schemes, these ways of combining functions together, and those ways of combining functions such as primitive recursion, composition, and minimization crucially relied on the basic notion of being functions of many arguments. But we also saw last week that these 2 approaches, so these are 2 approaches. We could call them approach A. So this is approaches to modeling the notion of computability. So we have approach A and approach B. But we also saw last week that the 2 approaches are fundamentally equivalent. And we did that by showing that if we define the notion of computable partial function on the natural numbers using Turing machines, using the representations from lecture 3, that gives us the same notion as the self-contained definition of the partial recursive functions. And let me just write it down. I mean, we did it last week. So the computable partial functions via approach A coincide with the partial recursive functions. Approach B. And because somehow the very term partial recursive functions is very tied down to the way of the particular way of defining it using primitive recursion, minimization, and composition. I mean, we've got two equivalent notions. I'm just going to favour, it doesn't matter which one we take as the primitive definition, as the definition that has priority, approach A or approach B, but I'm going to favour just talking about the computable partial functions, because now we're sort of appreciating it. We're appreciating that these are the partial functions that are computable according to any good notion of computability. We'll see much more evidence for that next week. So this is a sort of neutral name that's referring to the functions as they are, so to speak, without prejudicing one of the models that's used to define the partial functions. Okay, so we've got these two different approaches. So if, as we were doing, if we adopt approach A, which was what we were doing at the start. So we're talking about functions on words. We could nonetheless address what it means to be a computable function between other kinds of data using this idea of representations that we covered in lecture 3. So we cover computability on other data, words, using representations. And for this, we were representing the data from a countable set, or elements from a countable set. And the representation took us from a partial function going from words over an alphabet onto partial, onto a set X, which is the set of represented entities. And then we can talk about what it means for a function or a partial function from a represented set X to a represented set Y to be computable, what it means for a subset to be decidable, this sort of thing, using the notions of representation. So this is all in lecture 3. Suppose instead we took lecture 4 as the basic definition of computability. Then for free, we get the notion of what it means to be a computable partial function on natural numbers. And if we want to talk about computability on other data types than the natural numbers, well, if we're taking approach B as our basic definition, we somehow want to avoid referring to Turing machines and words there. So it's a natural thing to do is to tweak, that means modify a little bit, our definition of representation to, instead of representing elements by words, represent them by natural numbers. So if we adopt, so that the words are the same, if we adopt approach B, we can cover computability on other data than, well, than numbers in this case, because we're naturally given computability between numbers using, again, representations. But now our representations, so our representations in the first case were partial surjective functions from words onto the representing set that they're represented. Now we're going to use a different letter just to somehow separate them. So we're going to use rho. It's the Greek letter rho, which will try to distinguish it from my P's. My writing is not always perfect, as you know. Anyway, so we represent a set by now assigning to each, well, each element of the set is represented by a non-empty set of numbers represented. So the idea is we always want to represent by the basic data type that we're computing with. And if we adopt model B, the basic kind of data we're computing with is natural numbers rather than strings, so we represent things as natural numbers. It's not very hard to see that one can go from representations of the first form, the A representations, to the B representations, because for any finite alphabet, a set of words, or so that finite sequences over the finite alphabet, can easily be put in bijection in an easily computable bijection with the natural numbers, and vice versa. So using a computable bijection, of that's an isomorphism, if you like, a bijective function from the natural numbers, a set of words over a finite alphabet, one can easily change a B representation into an A representation and vice versa. So there's not really very much difference between the two ideas. One can change B representations into A representations and vice versa. But what I want to do now in the course is begin to start taking the computable functions on the natural numbers as the basic notion of computability. It has some advantages to it in that natural numbers are very, somehow the simplest mathematical entities you have, the first mathematical thing you learn about as a child. In some ways, it's a little bit quicker and neater often to give representations using natural numbers than words. Representations using words tend to be more humanly readable because, for example, when you're writing tuples to represent a product, you can separate them by commas and things like this and write them in the way that a human will read. But representation using natural numbers is easy to define, and it's just a mathematical thing. And as mathematical notation, it's somehow easy to manipulate and reason about. And also, books on computability theory tend to then develop the subject using, normally implicitly, but the notion of representation is not that often considered in books, but they tend to represent things. The books on computability tend to represent more interesting data using natural numbers. We're going to switch to this representation, in this kind of representation, in order to do this. So rather quickly, I'm just going to make some redefinitions, but I'm not going to go through all the details. I'm not going to define what it means for a function from a representation X to a representation Y to be computable again, because it's the same thing, you just change words over the alphabet sigma to natural numbers, and you replace Turing machine computable with a computable partial function on natural numbers. So that's the same thing, but what I want to do is just make some of the definitions with a couple of easy examples, and then use this to lead into an example that's not easy and is going to be the main subject of the lecture today. And then hopefully you'll see somehow the power of the approach. Oh, and I realized, so I did a whole lot of talking over there without moving the camera, the usual thing, but I can move the camera here while I'm erasing them. Oh. Oh, erasing this board can record that. Right, so I think henceforth in this course, although maybe I shall sometimes consider the word representations again, and if I do, then I'll explicitly say so, but if I don't, then we're going to redefine, so henceforth in the course, a representation of a necessarily countable set X is again, a surjective partial function rho, which goes from the natural numbers, so our names for elements of the set X are now natural numbers. To compute with elements of the set X, we compute with the name, the representing numbers that are representing those elements. So it's a surjective partial function. Well, that's it, that's the definition. Okay. So I'll just give 2 examples. So when we were representing the natural numbers using words, well, we considered 3 different representations, 2 different kinds of binary encodings and 1 unary encoding of natural numbers. If we want to represent the natural numbers using the natural numbers, there's of course nothing we need to do. So it's a trivial one, but the identity representation that rho sub n, which is just the identity function that maps a number to itself, which is a total surjective function around n. Okay, so not an exciting representation, but just computing with natural numbers doesn't really need a representation because we're taking now approach B, where natural numbers are the basic items that we compute with. More interesting, if we combine, we've got 2 representations of a set X and a set Y, then we often want to combine them to a representation of the product set. So given representations rho X, which is a representation of the set X, and rho Y, a representation of the set Y. Remember, this funny half partial arrow means it's a partial function, and the double bit means it's surjective onto, and this is supposed to be a set Y rather than a set X. Then the product representation of the set X times Y I'll call rho X times Y. So this is again a representation, so it wants to be a surjective partial function from the natural numbers now onto X times Y. So what we want to do is we want to consider how is it appropriate to represent pairs of elements, little x and little y, using a natural number here. Well, so representation of a little x belonging to the set X should be a name for it according to the representation rho sub x, so some number that gets mapped to it, and the same for a representation of a little y belonging to the set Y. And here we want to construct numbers that represent the pair. And the natural thing to use is, we already saw it last week, the pairing function on the natural numbers, so which was a very easily defined bijection on natural numbers that I defined last week, so I won't define it again, but its name was P. So our representation is going to be that rho X times Y of a number n. So we're going to consider a natural number n as being a representation of a pair little x, little y, is defined to be, so it's clearly equal to, it won't always be defined, it'll be defined to be the pair little x, little y, if n equals the pairing function applied to two numbers L and M, where L is a name for little x and M is a little name for y. Okay, so a name for the pair x, y consists of a pair coded using the pairing function of a name for x, L, and a name for y, M. So where L equals pi x of, sorry, this should be x equals rho sub x of L, and y equals rho. So that's just saying L is a name for x, and M is a name for y. And if there is, if there exists an L and M such that this holds, and otherwise, then the pairing representation is undefined. Okay. So maybe not as natural as separating things by commas, not as readable, but still, I mean, since we have a simple bijection, the p function, so this is the pairing function from last week, this p function here. The pairing function from last week. Since we have the pairing function, that's easily done. Okay. So I hope you get the idea. And I don't want to go through all the material on representations again. It can be adapted mutatis mutandis, which is a phrase that means with the necessary modifications. It basically goes through as written, making only the modifications that are forced upon you by the change from representing by words to the change of represented by numbers. So an exercise for the totally masochistic of you, rewrite lecture note 3 using natural number representations. Otherwise, instead of doing that, just make the necessary adaptations as you need them, which is what we're going to do. Anyway, so where I want to go with this is now to the first main content of the lecture, which is an interesting representation using the natural numbers. What I'm going to do is I'm going to represent the set of computable partial functions of arity K. So I think it's superscript K. Let me just check. Yep. Of the set, which I'm going to call, let's call it like this. Sorry, I'm going to call it comp n to the k arrows n of computable partial functions from n to the k to n. So we want to define the surjective function from the natural numbers that is onto the set of computable k-parity partial functions. And in fact, it's going to be defined as a total representation. So it's not just a partial surjective function, it's going to be a total surjective function. We define a total representation. So phi sub k, which goes from 10, keep the double arrowhead saying it's surjective onto computable partial functions. So let's think what we want to do. So what we want to do, we can think of this function here as enumerating the partial computable functions, the computable partial functions in a sequence. We've got phi superscript k equals 0, applied to 0. That's the first computable partial function. Phi superscript k applied to, sorry, there should be a k here. We're enumerating the k-ary partial functions. Phi superscript k applied to 1, that's the second k-ary computable partial function, and so on. So but the traditional thing is to give this argument as a subscript here. So the arity k is given as the superscript. I'm going to stay with the traditional notation. The argument, the name, is going to be given as a subscript. So phi of k 0, that's going to be the first one. Phi k 1, phi k 2, phi k 3, and so on. The total representation, so for every subscript n, or e, I'm going to use e for these subscripts, the arguments here, we get a computable partial function, and it's surjective. So every computable partial function, arity k, is going to appear in this sequence here. It might appear more than once. In fact, it will always appear infinitely many times around going to define it. Anyway, the point is every computable partial function appears in this representation. So the computable partial functions are countable. So this is a sequence containing every k-ary, so arity k argument, computable partial function. With repetitions. So how do we define this? I'm sort of trying to move away from the Turing machine model by considering computable partial functions on the natural numbers via their definition as the partial recursive functions as basic. And it would be possible to use that definition via the partial recursive functions as a basis for now doing this, defining this representation here. It would be possible to use that. However, I find doing that more cumbersome than what I'm going to do. So in order to make life as easy as possible, I'm actually going to use the Turing machine models to define this. We've already done the work with the Turing machine model that's going to allow us to do this easily. So I'm going to refer, so I emphasize it's not necessary, but for convenience, given what we've done so far in the course, it is helpful to use the Turing machine model to define this particular representation. So essentially, I mean, we find the consideration of representations a bit abstract. All we're doing is we want to define, in a nice way, a sequence of computable partial functions in a sort of uniform way that is going to include every computable partial function of arity k. So to define by superscript k, we're going to recall our definition of Turing machines. Sorry, not our definition, recall our encoding of Turing machines as streams. Not streams, strings, as words. Sorry, but our encoding of Turing machines as words. So remember, the notation was angle brackets of m is the encoding of a Turing machine m. This was a word over the universal alphabet, sigma u. So there's a word over that, where the universal alphabet was 0, 1, minus, I mean, just for convenience. We have square brackets, opening and closing them, it's double bar and book. So words over that alphabet. The details don't really matter anymore, we just need to remember that we did this. But having obtained this, it's very easy now to get a representation of Turing machines as numbers, using similar tricks to what we did last week for encoding words as numbers. So, so we simply rename these seven symbols 0 to 7, 0 to 6. So renaming the 7 symbols in the alphabet, in the universal alphabet, as the numbers 0 up to 6. And using our encoding last week of words of numbers as numbers, so we were encoding words of numbers as numbers. We get a number representing a Turing machine. We have a number. We simply take our word encoding the Turing machine and then encode that word as a number. So this is a natural number encoding the Turing machine M. Now the question is, where do I want? I can squeeze this in at the bottom of the board here. So what we want to do is define the k-ary partial computable function by superscript k applied to index e. Okay, so the index e element in the sequence, index 0 is the first one, index 1 is the second one, and so on. So, and we're going to use the Turing machine model to define this. So we define, so phi superscript k index e, we want this to be a computable partial function from n to the k to n as follows. So firstly, we need to define a partial function, and then we need to check that it's computable. It needs to be a k argument partial function. So phi to the k subscript e applied to x1 through to x1 through to xk It's defined to be, well, it's a partial function, so it's cleanly equal to. The point is we need to decide when it's defined, and if it's defined, we need to give it a number as a result. So we give it the value y, that's a natural number, if, I didn't move the, please people on Zoom, shout if I don't, maybe the volume's not. No, the volume is up. Please shout if I don't move the camera. Or well, there are 3 people there. They can't all have fallen asleep. Hopefully. So it's y if there exists a Turing machine M such that the number E is the number encoding M. So it's the number encoding the string representing the Turing machine M. And M halts in the halt state when run on input string binary representations of x1 through to xk separated by commas. The binary x1, comma, through to binary xk with the binary representation of y on the tape when it halts. So that's the result of the computation with binary y on the tape. And if it doesn't, if there is no such Turing machine, or there is such a Turing machine, but M doesn't halt in the halt state, or it does halt in the halt state, but it doesn't do the right thing. It doesn't halt with the binary representation of a number. In any of those cases, then the function's undefined. So the point is, we interpret E as a number that is a code for a Turing machine, a representation for a Turing machine, and then we say, well, phi superscript k of E is the k-array partial function that is computed by that Turing machine, if it computes a k-array partial function on natural numbers. In the case that it doesn't compute a k-array partial function on natural numbers, well, then we just diverge relevant inputs anyway. And this is enough to fulfill this condition. It's clear that every computable partial function of arity k is going to appear as as phi sub e for some e, because by definition, a computable partial function is computed by some Turing machine. So let E be the code of that Turing machine, and phi sub e, superscript k sub e, is then that computable partial function. Moreover, by the way we've defined it, every phi sub e, even when e is not the encoding of a Turing machine, is nonetheless a computable function. Because one can easily, basically one can compute this definition. So we have fulfilled our desire to give a representation, moreover defined on all numbers, of the computable partial function from n to the k. Okay. One way to look at it is abstractly as a representation. Another way to look at it is just as defining the sequence of all the k-array partial functions. The two are basically the same thing, and hopefully that very thought makes
representations seem a little less abstract. Obviously, it's break time because there's noise coming from outside. So, I mean, I make it 3 o'clock exact. Oh, the clock on the back wall is back. So there we are. We start at 15:15. Oh, it's 1 hour. Yes, so they haven't adjusted the time. Yeah, I don't want to take. I didn't take it off last time. I went within half a meter of it and it fell off. I'm not quite sure what happened, but anyway.